Here we are on page 4 of the chi-squared packet. And on page 4, we're going to be doing something a little bit different than before. We're using the chi-squared goodness of fit test, which is right underneath the chi-squared test, which we've been doing up until now. The main difference between chi-squared test and chi-squared goodness of fit test, and the way you're going to quickly identify which one you're going to use on the IB exam, is how is the data presented? Is the data presented as one column or one row of data? Or is it like the previous pages where they give you a matrix of data which is at least 2 by 2 large? Okay, and so like on this page you can see that all the problems are just one row or one column of data. So one of the matrix dimensions is 1. It's either 1 by 5 or it's 5 by 1. Okay, in this first problem, let's read it. Terry buys 10 packets of Skittles and counts how many of each color there are. In total, she has 600 sweets. According to the Skittles website, the colors should be evenly distributed with 20% of each color in each bag. The result for Terry's 10 bags are, and so Terry has counted up all the different colors and she's gotten this distribution here. What the Skittles website says she should expect is she should expect 20% of each color because there's 5 different colors, and the Skittles site says that they should be evenly distributed. Most of the problems you're going to do with chi-squared goodness of fit is going to be evenly distributed. So we have 1,200, or I'm sorry, I multiplied it times 6,000. It's actually multiplied times 600, right? 600 Skittles. So she's expecting to have 120 for each one of these elements, and instead she got numbers ranging from 98 to 137, right? Okay, find the expected frequencies. Okay, so we found the expected frequencies. They're right here. Okay, the expected frequencies are the same number for each color, 120. Write down the number of degrees of freedom. Okay, so here the number of degrees of freedom is 1 less than the total number in the row. So there's 5 numbers here, and the number of degrees of freedom is 4. Determine the results of a goodness of fit test at the 5% significance level to find out whether Terry's data fits a uniform distribution. Remember to write down the null and alternative hypothesis. So the null hypothesis in this case is that Terry's Skittles are distributed uniformly. So the key is that it's distributed uniformly. So write that the Skittles are distributed uniformly. That's the null hypothesis. The alternative hypothesis is that the Skittles are not distributed uniformly. Okay? So the critical value of the test is 9.488, and they want us to run the chi-squared goodness of fit test, and we do that not with second matrix. Since this is not a matrix, it's just a column, we're going to put it into stat edit. So into stat edit we put 2 columns of data. We're going to put the observed data in list 1, and then we're going to put our expected frequencies in list 2. So I'm going to do that offline so I don't bore you. Input the data. In list 1 there's the observed frequencies. In list 2 there are the expected frequencies. And we're going to run stat tests, chi-squared goodness of fit. And we're going to say list 1 for observed, list 2 for expected. The degrees of freedom is 4 because it's the number of elements minus 1. And then we calculate. So our chi-squared value is 10.45, and our p-value is 0.0335, and the chi-squared value of 10.45 is greater than the critical value, so the null hypothesis is rejected, and the p-value is 0.0335, which is less than the significance level, which is 5%, 0.05. And when it's less then the significance level, the null hypothesis is rejected. Because remember that as the chi-squared value goes up, the p-value goes down. So they're kind of inverses of each other. The rule is when the chi-squared value is greater than the critical value, the null hypothesis is rejected. When the p-value is less than the significance level converted to a decimal, then the null hypothesis is also rejected. Okay, let's go to number 2. There are 60 students in grade 12. Mr. Stewart asked them which month their birthdays are in, and the results are shown in the table below. So here is another distribution, which is just one row tall, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the number of months in a year, wide. So the months in which people have birthdays are uniformly distributed. Write down the table of expected values. So we have a total of 60 students. So if we take those 60 students and distribute them evenly throughout the 12 months, what we would expect to see is 5 students in each month. Okay, so that would be the table. It would be a bunch of 5s, 12 5s next to each other. Write down the number of degrees of freedom. It would be the 12 minus 1, because remember the way you figure out expected frequency is you figure out how many of these you're free to choose, which would be the first 11, and then the last one you would be forced to calculate by subtracting the total of the 11 months minus 60. So basically 12 minus 1 gives you the degrees of freedom, so it would be 11. Determine the results of a goodness of fit test at 10% significance level to find out whether the data fits a uniform distribution, and remember to write down the null and alternative hypothesis. So the null hypothesis is that the birthdays are distributed uniformly, and then the alternative hypothesis is that the birthdays are not distributed uniformly. Okay, the critical value of the test is 17.275. State the conclusion for the test and give a reason for your answer. So again, we're going to use the calculator here, and we're going to put the data into list 1 and list 2. In list 1, we're going to put the observed frequencies, 3, 5, 4, etc. And in list 2, we're going to put the expected frequencies, which is all 5, and we're going to have 12 data elements for each one. And I'm going to do this data input offline so I don't bore you. Put my data into list 1 and the list 2, and then I'm going to do stat tests, chi-squared goodness of fit, and L1 and L2 are already in observed and expected, and I do need to change the degrees of freedom to 11, which would be the number of months 12 minus 1. And then my result is the chi-squared value is 6. So the chi-squared value is 6, and the p-value is 0.873. And so the chi-squared value of 6 is less than the critical value of 17.275. So that means that the null hypothesis is accepted. And the p-value of 0.873 is greater than the significance level of 10%, or 0.10. So the null hypothesis is accepted also. Now they always should give you the same result. Okay, let's go to number 3. We are going to have more of these problems eventually because you can do chi-squared goodness of fit with different distributions other than the uniform distribution. It's just that we haven't learned any of the other distributions yet. So once we learn normal distribution and binomial distribution, which are other types of distributions that are commonly found in, naturally occurring or man-made phenomenon, you can also do it with that. But those kind of problems we'll do after we learn the other types of distributions. So here, this will be the last problem we do on goodness of fit. So Sergey works in a call center. 1 week he answers 840 calls. The number of calls that he answers each day are shown in the table. The calls are uniformly distributed. So 840 calls, to find the expected frequency, we would expect the 840 calls to be distributed evenly throughout the 7 days of the week. So 120 calls per day. So all the expected frequencies would be 120. So how do we show that it's 120? We would take 840 and divide by 7. That would give us 120. Write down the number of degrees of freedom. It's 7 days minus 1 day, so that would be 6 days. Determine the results of the goodness of fit test at 5% significance level to find out whether the data fits a uniform distribution. Remember to write the null and alternative hypothesis. Null and alternative hypothesis. The null hypothesis would be that the calls are uniformly distributed. And the alternative hypothesis at the calls are not uniformly distributed. The critical value for this test is 12.592. State the conclusion for the test and give a reason for your answer. So again, we're going to go into stat, edit L1, and we're going to put in the observed data, and then we're going to put in the uniformly distributed data. So we're going to put 146, 198, etc. in the first column, and in the second column we're just going to put a bunch of 120s, and I'm going to do that offline so that I don't bore you. And my observed data in list 1 and my expected data into list 2, and then I'm going to go and do stat tests, chi-squared goodness of fit, and then L1 and L2 are the default, so I just leave those there. The degrees of freedom in this case would be 7 days of the week minus 1, so it would be 6, and I press calculate, and the chi-squared value is quite big. It is 86.1, and the p-value is equal to something very small, 1.97 times 10 to the negative 16th. Okay, and in this particular case, the chi-squared value is much greater than the critical value of 12.592, right? So the null hypothesis is rejected. And same with the p-value. The p-value is much smaller than the significance level, which is 0.05. So again, the null hypothesis is rejected.